Hello everyone, welcome to the Mercury Virtual. Hope you are doing good. Today I am going to continue with your chapter number 11, that is concurrent programming. I hope you understood all the things that we have covered in this chapter, in the previous chapter. If you have any difficulties, anything, any issues, then please feel free to ask from me. Alright, so let's start the session. Today's topic is concurrent programming with the thread. In the last class we have discussed the concurrent programming with the processes, concurrent programming with input-output multiplexing. And today's topic is the continuation of the concurrent programming but with the threads. That is, processes and the input-output multiplexing is over. Now how to do the concurrent programming with the threads. But before this, let's take a quick review what we have covered in the last class, then continue with this topic, with the next topic, with this topic, that is concurrent programming with threads. So let's start with the last session, or let's start with the quick review of the last session. In the last class we have started with the chapter number 11, that is a concurrent programming. We have started with the concurrent programming with the processes, that is a concurrent processes. In this we have discussed about the introduction, that is what is the operating system and what is the programming, concurrent programming, how or what is the operating system, how one process can be handled or more than one process can be handled by the operating system. This is the introduction, that is modern operating system can handle more than one process at a time. That is, operating system can issue or can handle multi-programming at the same time or multi-processing at the same time. That is the more than one process at a time. In the same way, it is a role of the system scheduler to manage the processes and their competition for the CPU. That is, it is a role of the system scheduler to schedule the processes, to manage the processes for the CPU. Then again, it is a role of the memory manager is to manage or manage sharing of the main memory between the active processes. Then we have discussed what are the pros and cons, that is what are the advantages and the disadvantages of the concurrency. That is, first of all, advantages, that is concurrency is very good, or concurrency is good for the users, that is it is effective for the users. Why? Because with the help of concurrent programming or with the help of concurrent, it is the best, or it is the good reason for the multi-programming, that is more than one programs are executing at the same time with the help of the concurrency. Then we have discussed about the disadvantage. What is the disadvantage? It is a pain in the neck. Why? Because we have to access to shared data structure, deadlock, enabling process interaction. Then we also discuss about different concepts, that is what is a process, program counter, process context, execution context, concurrent program, multi-threaded program, parallel program. We discuss about definitions of all these things, that is what is a process, what is a program counter, what is the execution context, what is a concurrent programming, what is a multi-threaded program. Then we also discuss about the relationship between the processes, that is what is the relationship between among, or what is the relationship among different processes. Then we have discussed what are the resources that is available for the concurrent programming, that is if the processes are running in a concurrency, that is overlap with the time, what are the resources that is required for the concurrent programming. Then we have discussed that what is a mutual exclusive, that is two different processes are separate from each other, they are mutually separate from each other, that is known as the mutual exclusion, that gives rise to the problem which operating system must handle, that is a deadlock. Then we have discussed what is a deadlock, that is a condition where the same more than one process is approaching for the same resource. This says it is a process where a process is waiting for an event that will never occur. This is the example. There is a P1, this is the P2, one is holding the data, one is waiting for data, one is holding the data, one is waiting for data. Then these are the various attempts, these are the various issues that we have discussed. That is a mutual exclusion first attempt. This is the first attempt of the mutual exclusion. That is a busy waiting. Then coroutine we have discussed. We have discussed about the second attempt also. That is, what is the second attempt, or how we can achieve the second attempt. That is, each process can examine the other status but cannot alter it. That is, if there are 4 processes, that and then every process have a capability, have ability to examine the other status but cannot alter the status of other, but only examine, that is, see the status of the other one. If no other process is in the critical condition, critical section, then it stays set for the critical section. Then we have discussed about the third attempt, that is set the flag to enter the critical section before check other processes. Suppose there are 4 processes and the one process, let's example P1, P2, P3, P4, right? P2 is going to enter into the critical section. Then it must set the flag, that is, the operating system must set the flag for the P2. Why? Because it shows that P2 is going into the critical section, so that no other process is going in the critical section, do not get the time wastage. So this is the main issue, this is the main attempt how these issues can be resolved. Then we have discussed that a process sets its flag to indicate it desire to its enter or desire its enter in the critical section, but is prepared to reset the flag. Other processes are checked. If they are in the critical condition, the flag is reset. The correct solution is that each process gets a turn at the critical condition. That is, every process P1, P2, P3, P4 is going or have a turn. Turn means have an approach or have a turn every time whenever it goes to the critical condition. Means every process must go or must have ability to go to the critical condition one by one, but not all at the same time. Then what is a critical reason, or what is a critical reason? That is the area of a process which is sensitive to the IPC. That is the area which is critical, which is sensitive to the inter-process communication, that is known as the critical reason. This is the critical condition example. This is the process A, that is enter the, or A enter in the critical condition, critical reason. Then A leaves the critical condition, then B attempt to enter the critical condition, but till A leaves the critical condition, then only B enters into the critical condition, and then after the time interval, that is from T3 to T4, B leaves the critical condition. These are the 4 conditions to provide the mutual exclusion. Now, then we have discussed what is a semaphore. That is a system of communication using the flags, in which system or communication between the systems or the processes takes place with the help of the flags. There are 2 stations, that is the sender and the receiver, and they must be able to clearly see the other station. For larger or for long distances, they use the repeater, they use the router for sending or for communication between or among the different processes. What are the software that is used in the semaphore? That is a Dijkstra algorithm or Dijkstra software that is used in the 1965 that provides the semaphores as a solution. Then we have discussed about the file and the record locking. That is, what is the file locking, how file will be locked, and what is the record locking. This says mutual exclusion is required file processing where several users are accessing the same file. Example is airline booking system. Only one seat is left for the 2 agents that is accessing at the same time before file is updated and the seat is double booked. The solution is locking, preventing access to the file while it being updated. Then we also discuss about the types of file locking. That is, what are the types of the file locking that is available. One is file lock, one is read lock, one is write lock. In file lock, the file is locked, prevent from other processes from accessing any part of that file. Write log means other processes are able to modify as well as read the data of the file. And read log means only other processes can only read the file but cannot modify the content of the file. Then next topic that we have discussed is concurrent programming with the input-output multiplexing. That is, what is the input-output multiplexing? That is when an application needs to handle input-output descriptor, that is more than one input-output, then that is known as the input-output multiplexing. This is a non-forking concurrent server. There is an approach, there is a function that is used as the select function. Then we have discussed about the input-output models, that is blocking, non-blocking, input-output multiplexing, signal-driven, asynchronous. This is the scenario of the blocking input-output that we have discussed. Then non-blocking input-output. Then input-output multiplexing, that is how more than one input and output is given to the given at the same time. Then signal driven input output, that is what is a signal driven input output, asynchronous input output. Then select function, that how select function will be used for calling or for that allows a process to wait for an event that occur on any of the file descriptor. What are the events that occur? That is either read, write or exception condition. Then we also discuss about the struct FD set, that is file descriptor set. What is a macro? How concurrent server can be accessed. Then we will discuss about the socket options, that what is a socket options, what are the three options that is available for manage the sockets, that is get sock opt and set sock opt. One is FCNTL, one is IOCTL. These are the two functions, one is get sock opt, one is set sock opt. Then these are the various options, that is the socket options. One is SO broadcast, one is SO keep alive, one is linger, one is RCV buffer, one is RCV timeout. Then we will discuss about the next function, that is the FCNTL function. That's all for yesterday's session. This is the what we have discussed in the last class. Now let's start with the today's session, that is the today's scenario, that is concurrent programming with the threads. This says up to this point we have looked at two approaches for creating the concurrent logical flows. That is, till now we have discussed or we have gone through the two flows or the two methods or the two approaches for creating the concurrent logical flows. That is, with the first approach we use a separate process for each flow. That is, a separate process is used for each flow. That is concurrent programming with the processes. The kernel schedules the process. Each process has its own private address space, which makes it difficult for the flows to share the data. With the second approach, we create our own logical flows and use the input-output multiplexing to explicitly schedule the flows. Because there is only one process, flows share the entire address space. Now, this section introduces a third approach that is based on the threads. That is a hybrid of these two. Hybrid means combination of these two. Combination of the processes, combination of the input-output multiplexing. Now, what is a thread? A question arises in your mind. What is a thread? That is a logical flow that runs in the context of a process. That is, if a process is executing, then in that process, in execution phase, whenever a logical flow that is runs in the process, that is runs in the context of a process, that is known as the thread. So any flow that runs in the process, that is known as the thread. Thus far in this book, our program have consisted of single thread per process, that is a single flow in the every process. But modern system also allow, that is a today's system also allows us to write the programs that have multiple threads running concurrently in a single process. That is, more than one or more than one threads are running, or more than one threads are running concurrently, that it at the same time more than one threads are running in the same process, in a single process. Threads are scheduled automatically by the kernel. That is, it is a responsibility of the operating system to assign the kernel that threads are automatically assigned or automatically scheduled, that is provided by the kernel. Each thread has its own thread context, that is, every thread has a thread context logical flow, including a unique thread integer number or ID, that is a identification number, that is known as the TID, that is used for identifying the threads whenever there are multiple threads in a single process. Then there is a stack pointer, there is a program counter, there is a general purpose registers, and there is a condition codes. These are the multiple content, multiple features, multiple areas that the thread requires, or that thread has acquired. That is the thread context, unique integer thread identifier, that is the TID, stack pointer, program counter, general purpose registers, and the condition codes. All threads running in a process share the entire virtual address space. That is, every process or all the threads that is running or that runs in a process share the entire virtual address space of that process or that condition only. This says logical flow based on the threads combine qualities of the flow based on the processes and the input-output multiplexing. That is, every logical flow that is based on the threads combine the qualities or combine the or combination of the flow that is based on the processes as well as the input-output multiplexing. In simple terms, whenever we use the concurrent programming with threads, that is a combination of the concurrent programming with processes as well as the concurrent programming with input-output multiplexing. Like processes, threads are scheduled automatically by the kernel and are node to the kernel via integer ID. Like flow, based on input-output multiplexing, multiple threads runs in the context of a single process. That is, by the use of the process, every thread has a unique ID, that is a TID, and with the use of input-output multiplexing, multiple threads runs in the context of a single process and share the entire content of the process virtual space, including its data, including its heap, shared libraries, and the open files. Now, next is your thread execution model. That is, how thread will be executed. That is a thread execution model. Then 3.1 is thread execution model. That is, what is a model or how thread will be executing. That shows the thread execution model. This says the execution model for the multiple threads is similar in some way to the execution of the model for the multiple processes. That is how multiple processes are executed in the same way multiple threads are executing, that is in the similar manner. That is, it is very similar to the processes, that is the concurrent programming with the processes. Each process, consider the example in figure 12. This is the figure 12, this one. This is thread 1, that is a main thread. Then there is a thread 2, that is a thread peer thread. There is a time gap. This says each process begins with life as a single thread known as the main thread. At some point, the main thread creates a peer thread, and from this point in time, the two threads run concurrently. That is, first of all, whenever a thread occurs, the thread is called or going in the main thread. That is, it is available, or that a single thread is known as the main thread. Then sometime the main thread creates its own peer thread. Peer thread means at the same level thread. At that time, more than one thread, that is a peer thread as well as the main thread, runs in the concurrent way, that is runs in the concurrently. Eventually, the control passes to the peer thread via a context switch. That is how this control will be passed from this to this one. This is passed by using the thread context switch. because the main thread executes a slow system call such as read or sleep, or because it is interrupted by the system interval timer. The peer thread executes for a while before control passes back to the main thread, and so this is the condition why the main thread is passed to the peer thread. The main reason is that sometimes there is a delay in the main thread, so the control passes to the peer thread for the time being by the use of thread context switch, so that the peer thread will execute at the interval time, at the gap time, at the system interval time, and then again the control passes to the main thread, that is the thread 1. So this is the scenario, thread 1 and the thread 2 that runs concurrently at the same time, and the control is transferred and the control is passed by using the thread context switch. Thread execution is differs from the processes in some important ways. Because a thread context is much smaller than the process context, a thread context switch is faster than a process context switch. So this is a comparison between the thread context as well as the process context. So it says that the thread context is very faster as compared to the process context switch. Another difference is that thread, unlike processes, are not organized in a rigid parent-child hierarchy. That is, as we see in a process, there is a single process, there is a parent process, there is a child process, again there is a sub-child process. But this parent-child relationship is not available in the thread. That is, the thread associates with the process from a pool of peers that is independent of which each threads were created by which other threads. Next is POSIX threads, that is the P threads, is a standard interface for manipulating the threads from the C program. So if I am saying what is a P thread, that is a POSIX thread that provides a standard interface for manipulating the threads from the C programs. P threads defines about 60 functions that allows the program to create, to kill, to read, to share, to peer, to notify, and that allows the programmer to create these different entities, these different scenarios for the thread. This is the example how P thread will be created. This is the hello.c, hello world program. This says figure 13 show a simple P thread program. The main thread creates a peer thread and then waits for it to terminate. That is the main thread, that is the first thread, or the main thread creates a peer thread and then waits for it to terminate. The peer thread prints the hello world and terminate. When the main thread detects about the peer thread has terminated, then it terminates the process by calling the exit function. This is a scenario how P thread will be called, that is how POSIX thread will be called. Now let's see with the help of some PPTs what is the thread and what is the scenario how thread will be maintained. This is the chapter number 11 continue, that is a concurrent programming continued. The topic is concurrent programming with the threads, that is how concurrent programming is established with the threads. What is the main objective? Explain the parallel computing right from architecture or OS programming paradigm and the application, that is explain the various computing algorithm starting from the architecture, operating system, programming and the application. Then next objective is explain the multi-threading paradigm and all aspects of how to use it in application. That covers the MT concepts, issues related to the MT, Java threads, POSIX, API, Solaris, POSIX. Then debate on the MPP and the cluster computing. Now what is the agenda? First of all, overview of the computing, then what is the operating system issues, then threads basic, multi-threading, Java, distributed, grand challenges for Solaris, POSIX and Java example. So first of all, computing elements, that what are the computing elements that is available or that is that we have for the computation purpose. First of all, there is applications, that is applications are running in a computer like Office, Word, Excel, PowerPoint. Then programming paradigm, that is the programming base or the programming code that is used. Then operating system, that have a kernel, that have a system software. Then there is a hardware, that is a multiprocessor computing system. That is the hardware means different processor, different threads, different processes. Then what are the two eras of computing? That is a sequential era, that is a parallel era. In sequential, all the data is present in a sequence, that is a sequential era. Then parallel era, more than one processes are executing at the same time. Then history of the parallel processing, that what is the history? PP, that is a parallel processing, can be traced to a tablet dated around 100 BC. Now what is a motivating factor? Just as we learn to fly not by constructing a machine that flaps its wings with the birds, but by applying the aerodynamic, that is a aerodynamic principle demonstrated by the nature. We modeled PP, that is a parallel processing, after those of a biological species. Then what is the motivating factor? That is aggregate the speed, means increase the speed with the complex calculations. Then why we are using the parallel processing? That is why we are using the parallel processing. Computation requirements are ever increasing, that is distributed databases, scientific, that is earthquake, sequential architecture reaching physical limitation. Then what are the technical computing that is used? That is solving the technology problem using the computer modeling, simulation and the analysis. This is the computation or the computational power improvement. Now what are the processing elements? One is SIST, one is SIMD, one is MIST, one is MIMD. These are the various architecture of the SIMD, MIMD. Now, first of all, what are the threads? Thread is a piece of code that can be executed in occurrence with the other threads. That is, it is a piece of code or it is a type of code that can execute, that is a program in the context, that is a thread that can execute in occurrence or in concurrence with other threads. That is, more than one threads are executing at the same time. That is, it is a piece of code that can execute in a concurrence with other threads. It is a schedule entity on a processor. That is a schedule entity that is scheduled whenever it will apply on the processor. Then what are the thread objects? What are the contents that is available in the thread object? First of all, there is a hardware context, there is a registers, there is a status word, there is a program counter, there is a running condition. So these are the various thread objects that is available. One is your local state, one is your global, one is your PC, one is your hardware context. Then this is a threaded process model. This is a thread based model or thread process model, how they will be used or how they will be accessed. This is the shared memory, this is the thread stack, this is the thread data, this is the thread text. This is the threads within the process. These are the various levels of parallelism, that is how different levels of parallelism takes place. First of all, there is a task, there is a control, there is a data, there is a multiple issues. This is the example of the thread. Now, what are the various models or the various few popular thread models? One is POSIX, that is a P threads. Then what is a multithreading? That is more than one threads are used at the same time. That is a uniprocessor. that is concurrency versus the parallelism. This is the concurrency, that is more than one processor executing at the same time by the CPU. This is the time and there are multiple processes the same time. This is the same time and there are multiple processes, that is P1, P2 and P3. So more than one process are executing at the same time. That is known as the concurrency. This says number of simultaneous execution units is greater than number of CPU. This is the multi-threading multiprocessor, that is more than one threads are executing at the same time. This is the computational model. This is the general model of the thread model that cites the detail of the machine architecture, map the user threads, map the VM, virtual memory. Then there is a POSIX, that is a P thread, that is a process parallelism. That is next is a data parallelism. Then process and the threaded models. This is the code comparison. This is the most important one, that is a multi-threaded server. Now let's see with the help of book. This is the example that shows the P thread, that is a POSIX thread. This says the main thread creates a peer thread and then waits for it to terminate. Now how to create the threads? This says the threads creates another thread, or the thread creates other threads by calling the pthread_create function. So this is the function that is used for creating the thread. What is the function that is used is the pthread_create. This is the function that is used for creating the threads in the operating system. This is the example that shows how thread will be created. This is the first line, that is the hash includes pthread.h, that is the header file that is attached. Then use the type def, that is a type definition, void, pointer, function, void, pointer. That is define the void function, use the void pointer. And then use the int pthread_create, that is the pthread function is used, or the pthread_create function is used. So this is the same function, pthread_create. Then these are the arguments. One is use the TID, that is the thread identification, then attribute of the thread, then pointer of the attribute, function, void, argument. This returns the 0 if okay, non-zero on the error. The pthread_create function creates a new thread and runs the thread routine f in the context of the new thread. So this says the pthread_create function creates the thread or creates a new thread and runs the thread routine, and that is run the thread routine f in the context of the new thread and with an input argument of arg. Then the argument attribute, that is the ATTR can be used to change the default attribute. That is how to change the attribute. It may be read attribute, it may be write attribute, it may be execute attribute. Then changing these attributes is beyond our scope. In our example, we will always call the pthread_create with a null attribute. This is the null attribute, there is no attribute. Next point says when the pthread_creates returns argument TID contains the ID of the newly created thread. The new thread can determine its own thread by calling the pthread_self function. This is how different thread or one thread can be called by itself, that is the pthread_t, pthread_self. So in simple terms, how to create the thread? By using the function that is a pthread_create, and how one thread calls itself, that is more at the same time how one thread calls itself again and again by using the pthread_self function. Next, how to terminate the thread, that is the terminating the threads. A thread terminates in one of the following ways. That is, a thread can terminate in the implicit way as well as the explicit way. When the thread terminates in the implicit way, when its top down or top level threads return, that is, it will terminate in an implicit way when its top level thread routine returns. That is Then next is the thread terminate explicitly by calling the pthread exit function. So there are two scenarios. One is in an implicit way, one is in an explicit way. Whenever a thread terminate in an implicit way, whenever the top level threads are terminated, or whenever the top level threads are terminated automatically, then they are terminate in an explicit way by using the function, that is pthread underscore exit function. So there is a difference. For creation, the same concept pthread underscore, but then use a create. In terminating, use a pthread underscore exit function. If the main thread calls the pthread exit, it waits for the other peer thread to terminate and terminate the main thread and the entire process with the return of thread data. So this is the scenario how thread will be terminated. This is the example. The function that is used is pthread exit. Then one argument is used, that is a void thread return. Next point says some peer thread calls the Unix exit function. That is, some threads also calls the Unix exit function, which terminates the process and all threads associated with the process. Another thread, peer thread, terminates the current thread by calling the pthread cancel function with the ID of the current thread. This is again the scenario, pthread cancel. Then how to reap the terminated thread? That is reaping the terminated thread. Next is your reaping the terminated threads. That is how to remove the terminated thread. That is how to reap out, how to clean out the terminated threads. This says threads wait for other threads to terminate by calling the pthread join function. That is, the other threads or the one thread waits for the other thread to terminate, or other thread can be terminated by calling the pthread join function. This is the example. The same example is used. One is the same header file, that is a pthread.h, then int pthread join. This is the function that is used for terminating the other threads. Then use the arguments, that is a pthread TID, that is a unique identifier, that is a thread identifier. Then use the void thread return. This says the pthread join function blocks until thread TID terminate, assigns the void pointer, that is a generic pointer returned by the thread routine, to the location pointed to the or pointed by the thread returns, and then reaps any memory resource held by the terminated thread. This is a scenario. First of all, use the thread function or join function, and then reap the terminated thread if whenever that is terminated the scenario. Next, how to detaching the threads. This says at any point in time a thread is joinable or detached. A joinable thread can be reaped or killed by other threads. So this says any process or any thread can be joinable or thread at any point of time. A joinable thread can be reaped out. Can be reaped out means can be cleaned out and killed by other processes. Its memory resources such as the stack are not freed until it is reaped by another process. So these two lines says at any point of time, at any level of time, a thread is joinable or detached. That is, a thread is detached, that is removed, that is killed by the or killing the thread. Then whenever a thread is killed, then next process or its memory resources are not freed out. Why? Because until they are not reaped out, until they are not cleaned out, their memory cannot be retrieved, their memory cannot be good. So its memory resources are freed automatically by the system when it terminates. So it is reaped out automatically when it terminates automatically the threads. By default, threads are created joinable. In order to avoid the memory leaks, each joinable thread should either be explicitly reaped by other thread or detached by call to the pthread detach function. So for automatic clean out or for automatic remove the ripping out the threads, we use the detach function, that is a pthread underscore detach function. This is the example, pthread detach pthread tid. This says the pthread detach function detaches the joinable thread tid. The threads can be detached themselves by calling the pthread detach with an argument of self, that is a pthread self. Next is how to initialize the threads, that is how to initialize the threads in the how to initialize the threads in the operating system. The way or the function that is used to initialize the thread, that is known as the pthread once. This is the pthread once function, allows you to initialize the state associated with the thread routine. This is the pthread once that is used for the initializing the threads. The once control variable is a global or the static variable, that is the one control variable may be of static type or maybe of global type or global variable. Now what is the difference between the global and the static variable? The global variable can be accessed at any time, at any block, in any block, at any time. That is, it can be accessed by any function, any scenario, any variable. But static variable is initialized to 0 whenever it creates the new process. That is always initialized to pthread once in it. That is the static variable that is used on initializing the thread can be used by use the pthread once init function. The first time you call the pthread once with an argument of once control, it invokes the init routine, which is a function with no input argument that returns nothing. Now next is your concurrent server based on the threads. Now let's see PPTs. This is the cooperative threads. This is the code comparison independent threads, cooperative threads, that is making the file copy, then RPC. This is the multi-threading server, that is the same, the concurrent server based on the threads. So this is a multi-threaded server. First of all, there is a client process, that is the client is available. There is a client process, there is a server process. This is the server threads and there is a client threads. And there are two modes, one is user mode, one is kernel mode. The message is passed from the user mode to the kernel mode, that is from the client to the server by using the mediator that is known as the message passing facility. So message passing facility is a mediator that passes the message from the client to the server by enabling or by using two modes, or by enabling or detaching with the two modes, that is a user mode and the kernel mode. This is the client process, this is the client process, this is the server process, and this is the server threads. This is the message passing facility. There is a user mode, there is a kernel mode. Next, multi-threaded compiler. This is a compiler. First of all, there is a source code that is converted into the object code by using the multi-threaded compiler. This is a pre-processed thread, there is a compiler thread. These are the models that is used for the thread programming, that is a Bose-Worker model, PN model, threaded pipelining. So this is the concurrent server based on the thread. That is, a concurrent server means more than one server that is based on the threads. This says figure 14 shows the code for the concurrent echo server based on the thread. This is the figure 14. This shows the concurrent server. That is, the echo is used for the concurrent server, that is the echo server. Then int main arguments are used, the different scenarios or different variables are used. Then check the condition. If argc is not equals to 2, then printf the error, otherwise printf the port equals to ATOI argument v1. The overall structure is similar to the process-based design. This is the concurrent server is similar to what we have discussed in the process-based design, or what we have discussed is the concurrent programming with the process. The main thread or the unique thread, that is the main thread, repeatedly wait for a connection request and then creates a peer thread to handle the request. As I told you in the beginning, there are two types of thread. One is a main thread, one is a peer thread. Main thread is a thread that calls a peer thread for the time being and then transfer the control to the peer thread by using the context switching, by using the thread context switch. While the code looks simple, there are a couple of journal and somewhat subtle issues that we need to look more closely. The first issue is to pass the connected descriptor to the peer, then we call the pthread create. This says then we have the peer thread reference this pointer and assign it to a local variable. So this is the basic part is over. That is, the basic part means what is the thread, how to create, how to reap out, how to detach the thread, that is over. Now how to share the variables in a threaded program, that is how multiple variables can be shared in the threaded program. So let's see with the help of the PPTs. These are the working models. This says from the programmer perspective, one of the alternative aspect of thread is the ease with which multiple thread can share the same program variable. However, this sharing is very tricky. This says the various or the alternative aspect or the main aspect of thread is the ease with which multiple threads can share the same program variable or can share the same program. But this sharing is not easy, this sharing is tricky. In order to write the correctly threaded program, we must have a clear understanding of what we mean by sharing and how it works. There are some basic questions to work through in order to understand whether a variable in C program is shared or not. Means what are the basic questions, whether a variable is shared in the program or not. What are the questions? What is the underlying memory model for the threads? That is, what is the memory that is required for the thread? Given this model, what are the instances of the variable mapped to the memory? That is, what are the examples that is mapped, or that is what are the variable that is required that is mapped to the memory? Finally, how many thread reference each of these instance, that is how many instances are available for the thread. Next line says the variable is shared if and only if multiple thread reference some instance of the variable. To keep our discussion of sharing concrete, we will use the example of figure number 50. This is the example of sharing. This is example that illustrates different aspects of sharing. First of all, there is a void thread, void vargp, then char pointer ptr, that is a global variable. This means this global variable can be shared by all the blocks, by all the functions. This is the int main, then int I, pthread, tid, that is a thread ID identification is used. Then use the character message. What are the message? Hello from foo, hello from bar. Then message is going to the converted or going into the ptr. Then use the for function, use the 0 till n I++. Then use the pthread create function for creating the thread. Then use the exit function for removing the thread. Then use the void thread function, that is the thread variable. Then use the my id, then static ints count equals to 0. Then use the printf for printing the unique id for printing the thread variables. This says the main thread passes a unique ID to each peer thread, which uses the ID to print a personalized message. Then threads memory model. What is the thread memory model? This is a thread memory model. This says a pool of concurrent threads runs in the context of a process. That is, more than one process are executing at the same time. Each thread adds its own thread context, which includes a thread ID, stack pointer, program counter, condition codes, general purpose registers. Each thread shares the rest of the process with other process. That is, these are the various contexts, these are the various options that is available for the thread, like thread ID, stack pointer, program counter, condition code. This includes the entire user virtual address space, which consists of read-only text, write-only text, the heap. The threads also share the same set of open files. That is, this is the model, the sharing model, that is a thread memory model. That is, thread also shares the set of open files. In an operational case, it is impossible for one thread to read or write the register value of another thread. On the other hand, any thread can access any location in the shared virtual address. This is a scenario, or this is a condition, that is, one thread can share, or one thread is able to share the another thread. The memory model for the separate thread stack is not as clean. These stacks are always or continued in the stack area of the virtual address space. Next, memory variable to the or the mapping variable to the memory. That is, what are the variable that is used in the threads. But before this, let's take 5 to 10 minutes break and then come back, starting with this topic, that is memory variables to a mapping variables to a memory. That is, what are the variable that is used in the threads. So let's take 5 to 10 minutes break. Now let's start with the next one or next topic, that is a memory mapping to the or memory variables to the or mapping variables to the memory. That is, what are the variables that is available that is used for the mapping to the memory. This says variables in threaded C program are mapped to the virtual memory according to their storage classes. That is, a variable that is required or variable that is required in a threaded C program that is required for the threaded program are mapped to the virtual memory according to their storage class. That is, it depends on the storage class. These variables are used in a different way. What are the types of variable that is used is, first of all, there is a global variable. What is a global variable? That is any variable that is declared outside of the function. This is the most important part. That is, global variable is always declared at the outside of any function. Why it is declared outside? Because sorry. Why declare outside? Because global variable can be accessed by anyone in the program. That is, anyone means at any block of time or at any given point of time this global variable can be shared. And this says at runtime the read-write area of virtual memory contains exactly one instance of each global variable that can be referenced by any thread. That is, at the runtime, these global variable can be accessed or referenced by any thread at any given point of time. For example, the global PTR variable declared in the line 5 has one runtime instance in the read-write area of the virtual memory. So this says whenever we declare the global variable, that can be shared by anyone in the variable, and that can be and that global variable is declared outside the function. Then next is your local automatic variable. One is the global variable, then is the local variable that is declared inside a function without the static attribute. That is, without the static keyword, this global variable can be declared. At runtime, each thread stack contains its own instance of any local automatic variable. This is true even if multiple threads executes the same thread routine. That is, this is very true, or this is correct whenever multiple threads are executing at the same time, that is executing the same thread routine again and again. For example, there is one instance of the local variable, that is TID, and it resides on the stack of the main thread. We will denote this instance as a TID.m, that is a thread ID.m. We will denote these instances as a myid.pu and the myid.p1 respectively. Then next variable is the local static variable. So one is your global, that is declared outside the function, that can be shared or that can be accessible by any function, by any variable in the program. Then next is your local variable, that is the that resides or that is declared inside a function but without the static keyword, without the static variable attribute, and that function can be used only within the block of the function, only within the block in which it will be or in which it is declared. Then next is your local static variable, that is also declared within the function or inside the function but with the use of the static keyword, that is with the static attribute. As with global variable, the read-write area of virtual memory contains exactly one instance of each local static variable in a program. For example, even though each peer thread in our example program declares CNT in line 25 at runtime, each peer thread reads and writes this instance. Next topic is your shared variable. We will say that a variable V is shared if and only if its instances is referenced by more than one thread. We can say that a variable is shared only and only if the condition is that it is referenced or it is shared by one or more thread. It is shared by more than one thread. For example, CNT in our example is referenced or shared because it has only one runtime instance, and this runtime instance is referenced by both the peer threads. So this says a variable is said to be shared whenever it is referenced by more than one variable. Next topic is your fifth one is your synchronizing the threads with the semaphores. That is how semaphores is used, or how semaphores method is used to synchronize the threads. This says shared variable can be convenient, but they introduce the possibility of nasty synchronization errors. Before this, let's take a quick review of the PPT. This is the boss worker model, PM model, and the thread pipelining. This is what we have discussed. This is the synchronization, that is how to represent the thread events to indicates coincidence or coexistence. What is how the thread this is the definition of the synchronization. In the terms of Webster's, synchronization means to represent or arrange events to indicate coincidence or coexistence. That is, synchronization means representing or arranging the events to indicate whether there is any coincidence, whether there is any coexistence. In the terms of Lewis, to arrange the events so that they occur in a specified order. That is a synchronization. Next, serialized access to controlled resources. Synchronization is not just an empty issue. It is not even strictly an empty issue. Then how thread synchronization is performed. On shared memory, shared variable, semaphores is used for the thread synchronization. On the distributed memory within a task, how it will be or synchronization is maintained by using the semaphores, and across the task by using the or by passing the message between different processes. Then unsynchronized shared data is a formula for the disaster. That is the unsynchronized shared data, that is there is no synchronization but there is a shared data, that is also a disaster, that is also a mismatch. Then atomic actions, critical section. Then how to use a synchronization variable, what are the problems. Now let's discuss. This says shared variable can be convenient but they introduce the possibility of synchronization error. Consider the bad cnt.c program in figure 16. This is figure 16, that is a bad cnt program. Which creates two threads, each of which increments a global shared counter variable known as the CNT. That is, each of which increments or uses a global shared counter variable that is known as the CNT. Since each CNT increments the counter NIT ERS times, we expect that its final value to be 2 into NIT ERS. This seems quite simple and straightforward. Whenever we run the batch.cnt.c on our Linux system, we not get a wrong result, we get a difficult answer or different answer each time. This is the answer that is available. That means that gives a garbage values whenever we run these programs, because there is no synchronization. This is the improper synchronized counter programs. So what went wrong? To understand the problem clearly, we need to study the assembly code for the counter loop, that is a line 39 to 40 as shown in figure 17. We'll find it helpful to partition the loop code for the thread into 5 parts. One is H1, then L1, then UI, then SI, then TI. This is the head part, this is the load counter, this is the update counter, this is the store counter, and this is the tail. Notice that the head and the tail manipulate only local stack variables, while LI, UI and SI manipulates the content of the shared counter variable. This is the critical content, or this is the critical scenario. That is, in general, there is no way for you to predict whether the operating system will choose a correct ordering for your threads or not. That will be indicated by using the process graph. This is the process graph. This is the correct ordering. Now what is the process graph? That models the execution of n concurrent threads as a trajectory through an n-dimensional Cartesian scale or space. This is the figure that shows the graph, that is a process graph. There is a thread 1, there is a thread 2. This is L1, then S2. This is the L1, this is the L1 and the S2. Then this is the example of the trajectory. There is a H1, L1, U1. This is the graph that shows the execution, or that shows the transition from one state to the another state. This is the figure 20. Shows the trajectories that correspond to the following instruction ordering, that is H1, L1, U1, H2, L2, S1, then T1, U2, S2, T2. This is the scenario: H1, L1, U1, then L2, S1, T1, then U2, then S2, then T2. This says for thread I, the instruction L1 UI, LI UI SI that manipulates the content CNT constitutes an critical section. This is the safe and the unsafe transitory. This shows the safe and the unsafe. This is the safe trajectory, but this is the unsafe region. that shows the mutual exclusion. Then how semaphores is used, or how semaphore is used for the shared variables. This says at Jacob Disquestra, a pioneer of concurrent programming, proposed a classic solution to the problem of synchronizing different execution threads based on the special type of variable that is known as the semaphore. That is, in terms of concurrent programming, there is a problem, or that is a solution of the problem of synchronization that is given by the semaphores. A semaphore is a global variable with a non-negative integer value that can only be manipulated by two special operations, that is P and the V. So now let's see what are the two special operations, that is the P and the V. One is the P, one is the V. This says if S is non-zero, then P decrements the S and then return immediately. If S is 0, then suspend the thread until S becomes the non-zero. That is, this is a scenario. If the S is 0 and if the S is not 0. If it is 0, then it suspends the thread until S becomes non-zero. Otherwise, if S is already non-zero, then decrement the S and returns immediately. After restarting, whenever the S is 0, the P operation decrements the S and then return the control to the caller. So it depends on the S whether it is non-zero and whether it is 0. Then VS, that is the V operation, increments the S by 1. If there are any thread block at a P operation waiting for the S to become non-zero, then the V operation restarts exactly one of these threads, which then completes its P operation by decrementing the S. That is, it depends on the P, then V will be used by decrementing or incrementing the S by 1. The test and the decrement operations in P occur indivisibly, in the sense that once the semaphores become non-zero, then a decrement of the S occurs without the interruption. Thus, when several threads are waiting at a semaphore, you cannot predict that which one will be restarted at the result of the V. So it depends on So it depends on the P or the V values. The semaphores can be reduced or predict which one will be started at the same time. The definitions of P and V ensure that a running program can never enter a state where a properly initialized semaphore has a negative value. This says always the semaphore's value, that is the S value, is the positive. It cannot contains the negative values. This is the example, that is the hash includes semaphore.h. This is SEM init semaphore 0 uninitialized variables. Then how to use the semaphores for mutual exclusion. This is the synchronization variables in the semaphores. These are the shared variables, that is the global, local and the static variables. This is the mutuals, this is the synchronization variables. This is the problem. What is the problem? Deadlock, how to avoid, race conditions. Now, use the semaphores for the mutual exclusions. How semaphores provides a convenient way, that is the efficient way to ensure mutual exclusion access to the shared variable. That is, semaphores provides a convenient way to ensure mutual exclusive access to the shared variable. The basic idea is to associate a semaphore, that is S, initially 1 with each shared variable. That is, it associates or it uses the semaphore, that is S, initially at the 1 each with the shared variable. and then surround the corresponding critical section PS and the VS operation. That is uses the P as well as the S, that is the P operation as well as the V operation for the mutual exclusion, that uses the semaphores for the mutual exclusion. A semaphore that is used in this way to protect the shared variable is called a binary semaphores. That is the semaphore that is used to protect the shared variable, that is used by the shared variable, that is known as the binary semaphores. Why that is known as the binary semaphore? Because its value is always 0 or 1. That is because the binary value is 0 and 1. So any semaphore that uses the global variable, that uses the binary semaphores, that is always contain the 0 or 1. Binary semaphores purpose is to provide mutual exclusion, are often known as the mutexes. That is, the mutexes is used or mutex is used. Performing P operation on a mutex is known as the locking the mutex. Similarly, performing the V operation is known as the unlocking the mutex. So there are two types of operation for the mutual exclusion. One is P, one is V, and there is a binary semaphore that is using the zeros and ones for the semaphores. So if the locking operation, if the operation on P is P on the mutex, that is known as the locking, and the V operation is known as the unlocking the mutation or unlocking the mutex. A thread that has locked but not as unlock a mutex is known as holding the mutex. So one is lock, one is unlock, and one is known as the holding the mutex, that is neither locked neither unlocked. A semaphore that is used as a counter for a set of variable resource is known as the counting semaphore. Next paragraph says the process graph in figure 22 shows how use the binary semaphores. This is the how to use the binary semaphores, that is using the semaphores for the mutual exclusion. The infeasible states where S is less than 0 defines a forgiven or forbidden region that surrounds the unsafe region, that uses the unsafe region, and then prevents any unfeasible trajectory from touching the unsafe region. This is the unsafe region, this is the forbidden region. Initially S equals to 1, there is a thread 1, there is a thread 2. Finally, we protect the update of the shared CNT variable in the thread routine by surrounding it with the P and the V operations. Then it says when we run the properly synchronized program, it now produces the answer correct or the correct answer. Then how to use the semaphores to schedule the shared resources. This is one of the important concepts. So till now we have covered the topic, that is how to use a semaphore for the mutual exclusion. Now how to use a semaphore for the producer consumer problem. This says another important use of semaphores besides providing mutual exclusion, that is again the use of the semaphores besides the use of the mutual exclusion, is to schedule the access to the shared resources. That is, it is used for the or useful for the scheduling the access to the shared resources. In this scenario, a thread uses a semaphore operation to notify another thread. That is, a thread uses a semaphore or uses a semaphore operation to notify another thread that some condition in the program state has been true. Two classical examples are, or two classical forms or the operations are producer-consumer problem as well as the reader-writer's problem. So two types of approaches or examples included for that uses the semaphore for the shared resources are producer-consumer as well as the readers-writers. And the producer-consumer problem is shown in figure 23. This is the problem. There is a producer thread, there is a consumer thread, there is a bounded buffer. The producer generates the item and insert them into a bounded buffer. That is, the producer generates the item, it generates the variable, and then insert them into a bounded buffer. The consumer removes the item from the buffer and then consumes them. So it gives the item to this buffer, and this buffer that is, a producer uses or converts the things or converts the process into bounded buffer, then consumer consumes from the bounded buffer. This says a producer and consumer that thread shares a bounded buffer with n threads with n slots. The producer thread repeatedly produces the new item and inserts them in the buffer. That is, it produces the new item and inserts them in the buffer. The consumer threads repeatedly removes the item from the buffer and then consumes them. That is, first of all, producer produces the item and insert them in the buffer. The consumer removes the item from the buffer and consumes them. So this is a scenario how this will be maintained. Variant with multiple producers and consumers are also possible. That is, a variant means the variant that is available are also possible for the producer as well as for the consumer. Since inserting and removing items involve updating shared variable, we must guarantee mutually exclusion access to the buffer. Why? Because we are sharing the semaphores. So mutual exclusion is also there. That is, they are not mutually inclusive. That is, they are not mutually inclusive with each other. But guaranteeing mutual exclusion is not sufficient. We will also need to schedule access to the buffer. If the buffer is full, that is, there are no empty slots, then the producer must wait until a slot become available. Similarly, if the buffer is empty, there is no available item, then the consumer must wait until an item become available. This is the problem, that producer does not wait. They simply inserts the data even though it is filled. In the same way, consumer consumes the data even though it is empty. So it is a responsibility, it is a availability, or it is a problem that the producer fills the data even though it is full, and the consumer consumes the data even though it is empty. So this is the problem, and that problem is solved by using the semaphores. This is producer consumer interaction occurs frequently in a real system, in a real time. For example, in a multimedia system, the producer might encode video frames while the consumer decodes and renders them on the screen. The purpose of the buffer is to reduce jitter in the video stream caused by the data-dependent differences in the encoding and decoding times for the individual frames. The buffer provides a resolver slot for the encoded problem. So this says there is a comparison, there is interaction that occurs in the real system that is provided by the producer consumer. The purpose of the buffer is to reduce in the video stream by the data differences for the individual frames. The buffer provides a resolver slot to the producer for the encoding. Another common example is the design of the graphical user interface. The producer detects the mouse and keyboard events and inserts them into the buffer. The consumer removes the events from the buffer in the same priority it will enter in the screen. In this section, we will develop a simple package known as the S buffer for building the producer-consumer problem. In the next section, we will look out how to use it to build on an interesting concurrent server based on the threading. That is, use the server that is, or use the method that is known as the S buffer. So use the method that is known as the S buffer, only creates the problem. So producer consumer problem can be solved by using the S buffer, that is a S buffer, that is a buffer function that is used. Items are stored in a dynamically allocated integer array buff with the n items. The front and rear indices keeps track of the first and the last element. 3 semaphores synchronizes access to the buffer. Figure 25 shows the implementation of S buffer function. This is the implementation of S buffer function. One front is used, one rear is used. Then a binary semaphores is also used for looking for empty spaces. Now next is your reader writers problem. So this is the problem that is the next part of the synchronization that comes under the semaphores. So let's stop over here only. Let's stop over here only. This is the topic that I will discuss in the next class. So that's all. I think that's all for today's session. This is too over for the today's session because this is too much content that is available. So let's stop over here only, and I will discuss this problem in the next class, that is tomorrow's class. So that's all for today's session. But before finishing the session, let's take a quick review what we have covered in the today's class quickly for 2 minutes. We have started with the topic that is concurrent programming with the threads. That is how concurrent programming is achieved with the help of the threads. We have discussed about what is a thread, what is the thread context, what is a TID, that is a thread unit identification, that is a TID. Then this is a concurrent thread execution, that is how different threads are executed in a concurrent way. That is how one thread is executing with the another one, that is thread 1 and the thread 2. One is the main thread, one is the peer thread. Then we have discussed about the thread execution model. This is the same thread execution model. Then we have discussed about the P threads, that is the POSIX threads, that is the interface for manipulating the threads for the or from the C programs, that provides various functions like create, kill. Then we have discussed about how to create the threads, that is a function that is known as the pthread create function. Then we have discussed how to terminate the thread. Then how to reap the terminated thread, that is how to clean out the terminated thread. Then we have discussed how to detach the threads, that how to initialize the thread. Then a concurrent server based on the threads, that is how concurrent server is used based on the threads that is given. Then a shared variable in the threaded program, how to use the shared variable in the threaded program or threaded program, that is how variable can be shared in a threaded program. Then we have discussed about the thread memory model or the threading memory model that is used. Then mapping variables to the memory, that what are the variables that is used for the threading, that is local variable, static variable and the global variable. Then we have discussed about the shared variable, what is shared variable and how variable can be shared. Then we have discussed how to synchronize the threads with the semaphores, that is how semaphores can be used with the help of the, or how semaphores helps the thread synchronization. Then we have discussed about few examples, how what are the problem, or what is the where is the problem, and how semaphores will be used by using the process graph. Then we have discussed in detail what is a semaphores, what is the syntax of the S, what is the syntax of the P, how to lock, how to unlock, then how to use the semaphores for the mutual exclusion. Then how to use the semaphore to schedule the resources or schedule the shared resources. That contains two problems. One is a producer consumer problem, one is reader writer problem. In the today's class I have discussed only one problem, that is a producer consumer problem. In the next class I will discuss the reader writer problem. So that's all for today's session. Thank you so much everyone. Now if you have any doubts, then please feel free to ask the doubts and I will answer you. So that's all for today's session. Thank you so much everyone. Yeah, Larry, are you able to hear me?